Hi, this is another video in a series of chemistry videos of an introductory nature. This particular one is on the scientific method. Scientific method is a method that is based on evidence. So as human beings, we like to, we just know stuff. I got a good feeling about it. I have an intuition. My mom always said, those are all, sometimes we're right, sometimes we're wrong. Probably most of the time we're wrong. Science doesn't operate that way. Maybe you can make a discovery by chance, and there often are discoveries that are made on accident. But ideally, scientific method is used in science, and it's a method based on evidence, where we collect evidence and we form hypotheses based upon the evidence. Now, to be sure, make no mistake, all thinking starts with certain assumptions, certain things that can't be proven. Even science, when you boil science, all of it down, you end up with certain things that just can't be proven. You have to assume them. In geometry, we call these axioms. They are fundamental assumptions. And also, don't be mistaken, science does operate within certain paradigms that affect the kind of evidence you look for. So scientists don't just start out of the blue. I mean, they're looking for certain things when they go about doing investigations. And also, our paradigms affect the kind of hypotheses that we come up with to try to explain things. If I believe that the world is flat, then I'm going to interpret the evidence around other things from within a certain perspective. And so, even though science is based upon evidence, it's very clear, and you'll if you ever study the philosophy of science one day, you'll know that there are assumptions that are involved in science as well. We do have scientific paradigms. We undergo scientific revolutions in the way that we think about things. Nevertheless, science in its normal operating procedures tries to base what it thinks on evidence, not on assumptions, not on inference, not on intuitions, not on hunches or feelings, but on evidence. So, what we do is we observe, as scientists, a certain collection of evidence. We see something, we observe it. Then we form a hypothesis that might explain the evidence. Why did this happen when this happened? We kind of hypothesize a kind of cause-effect. What is the reason behind this? And then we test the evidence, maybe to confirm the hypothesis, perhaps to modify the hypothesis, or we can disprove the hypothesis. We do this all the time. Growing up in a family, let's say you had a brother or sister that you thought took something of yours. Well, you ask them, maybe you go to their room and look, and then you discover it was in your drawer all along. So we operate best when we make hypotheses to try to explain the evidence, and then we gather evidence, we experiment to see whether or not that hypothesis holds water or not. This is just good, ordinary thinking. The world would be a much better place if we all operated this way. What are experiments? Well, an experiment usually involves more than one variable to consider. The word variable, if you know the word variation, a variable is something, some aspect of evidence that can change. And there are often numerous variables that can be involved in a kind of event that takes place, or in chemistry, a reaction that takes place. So temperature could be a variable, pressure could be a variable, and such things. Usually you want to try to experiment on one variable at a time, and so you're probably going to keep the others the same when you're testing that one variable. So a control, if we talk about a control experiment, that's when we keep things the same. So if you're testing a new drug, you're going to have a control group that isn't getting any drug at all, or at least they may be getting a placebo that doesn't have any chemicals in it. And so you want to see whether the drug you're testing actually is what makes the change, or whether it's a coincidence from something else. An independent variable is the aspect of the experiment you are changing from experiment to experiment to see whether it's to blame, or to see what happens when it changes. So let's say you change the temperature. You keep everything else the same. You keep the pressure the same. You keep everything else the same, but you change the temperature. That makes temperature the independent variable. Then a dependent variable is the result that may vary depending on what we do with the independent variable. So maybe Maybe in one case it turns blue, in the other case it turns red. That dependent variable is dependent on us changing the independent variable. These are some things that are standard in the nature of experiments. So, let's say that we've observed something, we've created a hypothesis, we have experimented to see if the hypothesis holds true. After we have made a hypothesis and tested it over and over and over and over again, and still obtained the same result, we may be ready to formulate a theory. It's important, perhaps, to realize that in science, a theory is not a hypothesis. It's not a mere opinion. It's something that has been tested over and over again and continues to yield the same result. Or it's a theory that time after time after time after time seems to explain what you're looking at. Sometimes in popular language people will say, well, that's just a theory. You know, that's just the theory of evolution, or that's just the theory of climate change, or whatever. It's important to know that when scientists use the word theory, they have moved well beyond the hypothesis stage. That doesn't mean it's true necessarily, but it does mean that it's going to take an awful lot of new evidence, or something very, very, very major, some major new perspective, in order to change the general opinion of science about it. We don't in science call something a theory unless it has been tested and tested and tested and tested, either in experiment or, of course, you know, if you're talking about something of evolution, you're talking about something that looks at the past. Is that a different situation? It may or may not be, depending on your philosophy. But theory in that case is something that sufficiently explains the data that we have. But so anyway, a theory is not necessarily fact. It's not fact, in fact, but it is something that has been tested over and over again. We no longer in science use the word law. We don't come up with laws anymore. Scientists used to speak of scientific laws, laws of Newton, the laws of thermodynamics, but I think you'd be hard-pressed to find any new laws. We don't talk about the law of relativity even. We talk about the theory of relativity. Now, relativity that Einstein came up with has been incredibly successful at explaining things. Our GPS works on the theory of relativity, but they don't even call it a law of relativity anymore. So we've kind of, since the 20th century, given up on calling things laws, because we're more than ever aware that paradigms do, in fact, shift. And so even the laws of Newton are only laws for large objects. On the atomic level, they don't work. And at speeds approaching the speed of light, they don't work. And so if we were formulating the laws of Newton today, we would call them the theories of Newton. So, finally, what is a model? A model is a simplified representation that helps us grasp a situation that is much more complex. Our minds are not able there are many, many aspects of science today where our minds are simply not able, even the brightest minds, able really to contemplate things near the infinite, or things on incredibly vast scales. And so we use models to approximate things that are going on. So we might think of a surface as frictionless. There are no frictionless surfaces. We might think of a cable as being weightless. Well, there are no weightless cables. But the weight might be negligible, or the friction might be negligible under certain circumstances. This is going to drive certain personalities crazy. A lot of people who go into math or who go into science may go into it thinking, I want to know exactly. Well, you just can't. In many, many cases, you just can't. And so the Rutherford atom is a model of the atom. It helped explain some things, but then they moved on to the Bohr model of the atom when the Rutherford model didn't work. Is the Bohr atom now finally exact? No, it's not. And so we use models to try to get at complex realities by pictures that are much, the pictures of an atom that you have in a chemistry textbook are not exactly what an atom looks like. In fact, I'm not even sure what it means to say what an atom's look like. It's so small that light photons would completely destroy it, if you even tried to introduce that many photons there. And so we use models, abstract models, to try to get our heads around what's going on, even though it's not an exact representation. Computers, of course, can do things that humans can't. Computers can process millions and millions of variables, and they can do processing at the speed of light, at the speed of electrons. And so this is why some scientists are afraid of artificial intelligence in the future, because the kinds of calculations that we take, it would take us a whole lifetime to do, a computer can do in a matter of seconds. And so if a computer ever were able to think in any kind of analogous way to human thinking, they would so far surpass us, it would not even be funny. It wouldn't be any competition. But we use computer models to try to contemplate how weather is going to change. You can maybe hear the wind. I may be rained on in a second. So there are computer models that try to process millions and millions of bits of data to predict what the weather is going to be like. As of yet, they're still quite off much of the time. I think there's a 30% chance of rain today, and yet it's looking like, again, the computer models are off. Need more computer space. This has been Scientific Method.